All right, how's everyone feeling today? All right, today's lesson is about standing waves. And hopefully by the time you leave here today, you'll have a better understanding of what standing waves are. I thought we'd talk about what standing waves aren't. That is not a standing wave, ladies and gentlemen. That's a person standing on a wave, but the wave is actually moving forward. Not a standing wave. However, if you play a music instrument, in every music instrument there's a standing wave that gets formed, which ultimately produces the sound, which everyone else gets to enjoy. So, let's look at this computer simulation showing the difference between a standing wave and a traveling wave. So that top wave there, that blue wave, that's a traveling wave. You can see it's traveling to the right. You know, if I follow my pen along here, see, it's moving to the right. It's moving from one place to another. Yes? You with me? Traveling wave. Let's look at the other wave. That's also a traveling wave. It's traveling in the opposite direction. Traveling down this old road. But if both waves travel through each other, the interference pattern that gets produced forms a wave that appears to be standing still. The red one down here, the resultant wave, is the superpositioning of the top two waves happening at the same time. So if I turn the other wave back on, and then I turn on the superpositioning, the resultant wave, if those two waves were passing through each other, sharing the same space at the same time, that is the wave that you would get. And notice, it's just like going wah, 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 up and down. It's like, here's a crest. Oh, no, that's a trough right there. No, that's a crest right there. No. You know, but it doesn't appear to be moving, that red wave. It's not like moving down the line. It's just kind of like standing still. It's like a standing still wave, as opposed to the blue and the green wave up above. Those waves are traveling waves from one place to another. This one down here, though, that red one, the interference pattern, when the other two share the same space at the same time, form that standing wave. So that's what this lesson is all about. These standing waves down below. I have another computer simulation here. Again, the blue wave is going to the right. This time the red wave is moving to the left. If those two waves were sharing the same space at the same time, the black wave below is what you would end up seeing. That's the interference pattern. Here they come again. Once the interference pattern fully develops, it becomes a standing wave. So, how do you get the waves to stand still? They don't really stand still, people. the interference between the original waves and reflected waves ends up making the wave appear to stand still. Anytime you see a standing wave, you need to realize what's really happening is there are two traveling waves moving through each other, producing that interference pattern. Another key part of the process is reflection. The original waves get reflected back, as we'll see shortly. First, some background information on waves. What factors affect how fast a wave travels down a string? Everyone remember one factor that affects Nicole. The tension in the string. Excellent. And if there's more tension, does the wave travel faster or slower? Faster. Excellent. Does anyone remember the other factor? It's actually not called the coefficient, it's just the linear density. Okay? The linear density of the string. If it's a fat, hefty string, the wave's going to travel slower. So we could put those two together. Whoopsie, wrong button. And we get the velocity of the wave traveling down the string is equal to the square root of the tension divided by the linear density mu. And the linear density mu is equal to the mass of the whole string divided by the length of the whole string. Let's move on to some more class from the past. Reflection of waves on a string. Oh boy. This is a torsional wave. There's a long wire, and basically attached to that long wire are these pegs. And if you twist the wire, the pegs attached flare up and down. And if you only look at the tips, of the pegs, you're basically looking at a transverse wave. And notice when that original crest flies down and hits that fixed end, how does it end up reflecting back? Watch again. Whoopsie. Oh, brother. One moment. Very much awkward. Okay. This is the second video we want to see. Here we go. Do you guys catch that? You see what you're supposed to be seeing or not really?
Yeah.
Let me point it out to you a little more. Where's my pen? Oh, there it is. Okay. Don't hit the wrong button, then I'll have to sign back in. Here comes the crest. But right when the crest hits here, notice how it goes back as a trough. Crest, 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 hits, goes back as a trough first. Did you see that? Here comes the crest, hits, flips back as a trough. What's behind the crest? A little bitty trough. How does that end up going back? Little bitty crest. Do you see the phase change there, folks? Okay. Now, what kind of an endpoint did we have just there? A fixed endpoint. This next one shows a loose endpoint. Once again, let's go back and watch the fixed endpoint. See how there's a little thing right here holding it down? And you have that phase change. Here comes the crest. It hits, it goes back as a trough. Now, this next one, oh! Did you catch it? Here comes the crest out front, hits the loose end, flares up. What ends up going back? A crest. Oh dear. Replay. Here comes the crest, loose end. What ends up going back? A crest. Here comes the crest in slow motion. The end flares up loose, and the crest ends up going back. You gotta give me one of these apparatus there. That's pretty cool. Alright, enough of that. So, recall if the two waves hitting each other are both crests, they hit in the middle, they make a bigger crest. Constructive interference. If you have a crest and a trough hit each other, what ends up happening? They cancel each other out in the middle. Destructive interference. Now we're finally ready to make a standing wave. Yoo-hoo! Jibaloo! Okay. Scene 1, you have a wave traveling down a string. It's moving to the right. This end over here is fixed. Ultimately, the other end will be fixed as well. Scene 2, a moment later, that wave travels a bit farther down to the right. It'll be right in the middle of the string, that crest. So that's the same string with the wave just moved a little bit further down to the right. Scene 3. You're right, you guessed it. That same wave moves a little bit closer to the wall. Just about ready to hit the wall. And finally, scene 4, the wave hits the wall, but how does it reflect back? Jeremy? As a trough. Goes through a phase change because it's a fixed end. So let me make some space. For my next scene. Scene 4. Now before you draw all of scene 4, you might want to watch, because we're about to play a dirty trick on that reflected trough. Here's the end point over on the right. This wave right here, scene 3, womp, 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 meow, womp, womp, womp. That wave hits the wall, flips, and goes back as a trough. No surprise there, seen it. So there's that first wave, headed back. But we now send another crest down to meet it. That's right, Nicole. As the trough is returning, we send a second crest down, and you know what's going to happen in the next scene. Oh yeah. We send a second crest of equal amplitude down the string. Timing is everything, because we have to send that second crest exactly when the first crest starts its journey back. So you see, reflection is a big part of the standing wave. And here comes the interference. Let me make room for my scene 5. And I want you guys to draw what scene 5 will look like. I'll come around, you get thumbs up, thumbs down. A person sent down a second wave. Or your physics machine. Is that it? That's exactly what I'm talking about. in the middle. The next scene is when both of them are in the middle. That's what I'm talking about. Yes, that is it.
Is it possible to send a crest without sending any kind of trough?
Is it possible to send a crest? Yes. Yes. We're going to do that in a moment. Sometimes it's referred to as a pulse. That's what I'm talking about. That's what I'm talking about. The next scene. No wave. No way. No, really. No wave. No way. Really. The two waves cancel each other out due to destructive interference. Now, a moment later, they reappear like two invisible ships crossing through each other in the night. Scene 6. You see this trough right here? It was just in the middle here, but it got canceled out. Now it's going to be on the left over here. You see this? Let me try to draw a little bit. So there's that crest here. And then it was going in the middle here, but it got canceled out, and now it's right here. This crest here. Going to the right here. Traveling through the middle here, got canceled out. Where does it reappear? Over here. Now remember, both endpoints are going to be behaving like fixed endpoints. So there's our scene 6. Now when both of those waves hit the endpoints, what's going to end up happening to both of them? Joey? They're both going to reflect back, but more than that, they're both going to go through a phase change. And scene 7 is going to look like a previous scene. That's still up there. What's scene 7 going to end up looking like? Michelle? Scene 4. Because this one right here hits the wall and flips back as a crest. This one right here hits the wall, flips back as a trough. So basically I could just draw a big fat arrow and say, hey, the next scene, right back up to there. And then the same pattern keeps happening. The two keep crisscrossing through each other, and you get this wave pattern right here. If you look carefully, folks, is the string right there going up and down? No. Is the string right here going up and down? Is the string right here going up and down? No. So the string there in the middle no longer appears to be moving up and down. And even though there's these two waves traveling through each other, the end result is this. It ends up looking like this. You see this one moment of time. Then you see this the next moment of time. Then you see this the next moment of time. But this point in the middle never goes up or down. Sometimes these three diagrams are superimposed over each other. So sometimes the standing wave, all three scenes are shown on one diagram like this. One moment you see this. The next moment you see that. The next moment you see that. The three endpoints, the two endpoints and that point there in the middle are not even going up or down. So I want to demonstrate this to you. Okay, let's take a look at this, folks. I could send a crest down, it hits the fixed end, and it reflects back to me as a trough. I could send a trough down there, hits the fixed end, comes back as a crest. I can flip the whole thing up to send the crest down. And basically what I'm going to try to do is get the timing right and send down a crest, and right as it flips and starts coming back as a trough, I'm going to send down a second crest. Here it goes. And you end up getting a standing wave. Basically, it no longer looks like a traveling wave going from me down to Rajiv. It just looks like two sides bobbing up and down, and a point in the middle that's not going up and down at all. There's a special name for that point in the middle where there's no wave. It's called a nodal point. Same thing with the endpoints. Since the endpoints aren't flaring up and down, they're also called nodal points. Is that in the video? All right, thank you.
She's so cool. It's not like a crush. It's like a... No, it's a little crush.
Two already? Oh.
So that point in the middle is a nodal point due to destructive interference. And both endpoints are nodal points because they're fixed in place. Fixed endpoints are nodal points. Now the points in between the nodal points that are flaring up and down, they have a special name too. This is one single point. This one here and that right there. Because this same point will be here. A moment later it'll be there. A moment later it'll be back there. So this same point going up and down, that point, which is also that point, is an antinodal point. And this point over here, that's down here and then back up and then down here and then back up, flaring up and down, that's another antinodal point. So this wave pattern has 3 nodal points and 2 antinodal points. Sometimes people think that it's 4 antinodal points, but it's only 2 antinodal points because it's the same point that's flaring up and down. What we're going to do next, folks, instead of me sending down a single crest as that first trough returns, I'm going to send down 2 crests. So that first trough is going to be returning back. Let's go back. That first trough is going to be on its way back right here. But I'm going to have to pick up the frequency, and I'm not going to send just one. I'm going to send 2 of those crests down the line as that one crest is coming back. So, guess how many nodal points are going to be in the middle this time? No, just a new increased frequency, but not increasing. You know, I just got to pick up the pace and then stay at that picked up pace. So, Chief, you want to help me out here? Okay, so I'm going to send down a crest, comes back as a trough. But this time, when it comes back as a trough, I'm going to send down 2 more crests and keep that pace up. Do I got it? Oh yeah, there it is. 2 nodal points inside. Four nodal points total. 2 nodal points in the middle due to destructive interference. How many antinodal points? 3. Oh my goodness, you're not thinking what I'm thinking.
Oh my God.
What if I... Roger? What if I send down 3 crests while that sucker returns?
All right, okay.
Did I do it? I think the record is 6 antinodes. Let me see if I could match it. How many antinodes are there? 4. I think I've seen students do 6. Anybody want to give it a try? Michelle? Jeremy. Jeremy spoken.
Ready? Go.
Holy smoly. Now, can he beat the school record, ladies and gentlemen?
Alright, ready?
That's not happening.
Okay, come on.
Ready?
We do this. We do this.
Nah, I can't beat 6.
Try again?
One more time.
Jeremy said Martin Luther King was up.
You can't say that.
Nah.
Indeed. Let's see what you got.
Okay.
That's relatively unimpressive.
No dissing.
I bet Miss Kelly could come in here just like do 8.
Yeah.
Good job. Okay. Now, I think I'm going to pause the lesson here